Okay, this is basic statistics. We're looking at the chapter 7 notes, and we're looking now at chapter 7.3 and 7.4. So, assumptions for finding a confidence interval for a mean when population standard deviation is unknown. So the sample is a random sample, and n is greater than or equal to 30, or population is normally distributed when n is less than 30. All right, so now B, it says formula. This formula, we already actually used it on 7.2, but we'll write it down here. Again, this is X bar, so this is under B for formula. Let's write down the formula. X bar minus, this is going to be a t distribution because we don't have the standard deviation of the population. We only have the standard deviation of the sample, so we have to use the t distribution, not the z. Z has a pointier curve. It goes up higher. T is a flattened curve. So we had this down, like I said, on 7.2. All right? And a reminder, this value that we calculate is referred to as the margin of error. I think your book only calls it error. They might just call it E. I like Mo. Hey, Mo! Like the Three Stooges, all right? So now let's do the example on page 5 of your note packet. It says a random sample of high temperatures for 12 recent Thanksgiving days had an average of 42 degrees Fahrenheit. So they gave us an X bar of 42 degrees. They said the standard deviation of the sample was 8. So that's S. We don't get to use sigma. Sigma is what we use for population. S is what we use for a sample. Standard deviation is 8. And N is 12. They did 12 Thanksgiving days. And they would like a 95% confidence interval. So we're trying to build a 95% confidence interval. That means we're going to have to look up our t-score. Oh, just a reminder, don't freak out about this alpha over 2. Don't worry about that. It's a t-score, just like a z-score or a t-score. So I don't want you worried about the alpha over 2. That just means on the very first page when we drew the picture and I showed you 95% confidence, it was in the middle. And so that just means it's split into the two tails. But that's already built into our formula sheet. So you don't have to really worry about that. Just think of it as a t-score. So we want to find the t-score for 95%. So you go to 95% on table F. You go to 95%. And now you follow that down. Degrees of freedom are going to be 11. So n is equal to 12, which means degrees of freedom is always 1 minus. So that's 11 for our degrees of freedom. So that's what we're looking up on the chart for the t-score. So 95% confidence. 95% confidence, and we go down to 11 and follow that over 2.201. 2.201. 95% confidence with 11. All right? So let's write that down for our t-score is 2.201. Okay, and now it's just plug and chug from there. So we plug in X bar is 42 minus 2.201 times 8 over the square root of 12, which is less than mu, which is less than 42, plus all that same stuff, 2.201 times 8 over the square root of 12. So here, let's make quick work of this. We'll round to tenths right away. So when I multiply all that out and round to tenths, I get 5.1. So I got 42 minus 5.1 as my margin of error, and 42 plus 5.1. And so that means if we wanted a range for a 95% confidence interval, 36.9 is less than mu, which is less than 47.1. That's our 95% confidence interval. What does that mean? 95% confident that the population mean temperature will be between 36.9 and 47.1. All right, what that means is if we redid this 100 times, 95 of the 100 would capture the true mean and 5 would not. So you can say that you're 95% confident that the population mean will be between this and this. All right? But don't say things like we're 95% sure that the temperature is, because that's different. That's a subtle difference. But to say 95% confident that the population mean temperature will be between those two numbers is different than just saying, oh yeah, we're 95% sure that's the temperature. All right? Okay. So let's look at 7.4, the last page of these notes. So again, there's a blank thing for formulas. So we're going to skip up to the top. And we're going to look at the formulas for probabilities. And so probabilities, P. So we're looking at 7.4, top of the page, 7.4. Confidence intervals and sample sizes for proportions or probabilities. All right, so look. When we say P hat, that's read P hat. P hat is going to be the probability of an event occurring. Q hat is going to be 1 minus P hat, and that will be the probability of an event not occurring. All right. And so when we look at the formula for this, see if this looks familiar. It should look pretty familiar. P hat minus our z-score. So we're back to z land. You don't have to worry about t's for this. The square root of P hat Q hat divided by n. So that's all under the square root sign. You take P hat times Q hat, you divide it by the number of trials, and take the square root of the result and multiply it by that. So this is, again, the margin of error. This piece is the margin of error. We're finding P. When this is P, that's the proportion for the population proportion. And then this is just the same thing, P hat, Q hat, or n, all under the square root sign. All right? So let's look at some examples. Number 1. They want us to find, in a recent survey, 150 households, 54 had central air. Find P hat and Q hat. All right, so to find P hat, what you're going to do is just say, okay, well, 54 out of 150, that's 0.36. 36%. And 36% of the households have central air. Q hat then is going to be 1 minus 0.36 or 0.64. 64% of all those households would not have central air. And so that's p hat and q hat hopefully are pretty easy to find. Now let's do a problem where we get to apply this formula. On the next one, it says a sample of 500 nursing applications includes 60 from men. Find 90% confidence interval of the true proportion of men who applied to the nursing program. Okay, so they want 90% confidence. Let's erase this. So we're going to need some room. All right. So number 2 is going to look like this. First, let's find p hat. That's 60 out of 500. That's 12%, 0.12. That means q hat is 1 minus 0.12, so 0.88. So 12% are men, 88% are not men. And now what else do we need? We need 90% confidence interval, and we get to go back to z-scores. So we don't have to find degrees of freedom. You don't have to worry about the 500. You're going to go to your chart, table F on your sheets, and we're going to find 90%. Go to the top, it says confidence intervals, find 90%, and then take that all the way down to z. So all the way down to z is 1.645. So that's what we're going to use, 1.645. All right. And now we're going to put it into this equation. And again, do not be intimidated by these equations, because it looks really overwhelming if you look at it all at once. But if you really think about it here, all we're doing is plug and chug, and it's really just 4 variables that we're putting in and working out. Okay? So just the one that we did above. I omitted the little alpha over 2. You really don't need the little alpha over 2. It's built into our chart already that it's a two-tailed test, so you don't have to worry about that. So just z is fine. So now let's put in all of our information. We got 0.12 minus z, 1.645, times the square root of 0.12 times 0.88 divided by, what is that, 500, right? It's less than p, which is less than p hat, plus, now instead of writing this all out again, let's calculate this. This is our margin of error. So to calculate this, you're going to want to figure this out first. So you're going to want to do 0.12 times 0.88 divided by 500, take the square root of that. So here, let me do that. That's 0.12 times 0.88 divided by 500, hit enter. That's a really small number. That's 0.0002112. And then take the square root of that answer. And so this part of it works out to be 0.014537. And there's still more after it, I just stopped. Times 1.645. And when we multiply those two together, the 1.645 times that, we get 0.0239. We'll go out 4 places after the decimal. So that, this 0.0239 is my margin of error right here. This little piece of the puzzle is the margin of error. So the 0.0239 is the margin of error. So we're going to put that in right there. That is 12 plus 39. All right. And so now when we add those on, we get this. We get 0.12 minus 0.02 and 0.12 plus 0.02. It's about from 10 to 14. Here, let's see. We got 0.0961 is less than P, which is less than 0.1439. So when you have it on a test, I'll tell you, oh, round to hundredths place. All right, so to round this to hundredths place, we would go tenths, hundredths. So we'd look at that. That would bump it up to 0.10 is less than P, which is less than 0.14. So our 90% confidence interval would put the male nurses between 10 and 14%. Okay? Let's look at number 3 on that same page. A researcher wishes to estimate with 95% confidence the number of people who own a home computer. Oh, this is old because everybody, hopefully, pretty close to everybody owns a home computer. A previous study shows that 40% of those interviewed had a home computer. Researchers wish to be accurate within 2% of the true proportion. Find the minimum sample size that's necessary. Okay. So they want to know how big we have to take a sample if you want to have a 2% margin of error. And so, again, in some courses, like if this were an algebra course, I'd make you work backwards from what we know, but this isn't an algebra course. So all you have to do is find the correct equation sample size for proportion. And so if you take a look on the important formulas on the very first page where it's got all the chapters, it's run down by chapter. By chapter 7 near the bottom, it's N is equal to P hat Q hat times Z over error squared. All right. So let's write that formula down here for number 3. And the number that you have to survey, basically, P hat, Q hat. And again, they have the Z alpha over 2. Don't worry about that. Just call it Z. Error and squared. All right. And so let's see what they got. It says they want 95% confidence. So when we look up 95% confidence and we find the Z-score that matches with that, we use the chart. We go all the way down to the bottom. Z is equal to 1.960. All right. So that's what we're putting in right there. P hat and Q hat. Let's see. They gave us 40%. 40% of the people interviewed had a computer. So 40%. And then 60% is going to be the Q. Because remember, if P hat is 0.40, then Q hat is 1 minus 0.40, 0.60. All right, so we got that given. That we figured out. That we looked up on our chart. This error is, they want no more than a 2% error. Well, again, to play with the real numbers, you got to make that into a decimal. Remember, percents, it's always 2 places to the left to make it into a decimal. And then we square that result. So when you multiply all that out, you type that, you can type that into your calculator as it stands. You could divide this first, square the result, multiply the result by 0.6, multiply by 0.4. You end up with this answer, 2304.96. So we'll call it 2,305. You need to have your sample size to be 2305 people surveyed if you want to get it down to a 2% error on your confidence interval, being 95% confident. All right. And so they do this. This calculation is done a lot where if you want to, if you're going to report a certain thing, they did that. They'll do that again with the upcoming presidential election. They'll poll people, and they want to have. You'll see on the bottom of those little polls now. You can look and say it's 90% confident or 95% confident. And again, there's no guarantee that it isn't one of the stinkers. And also with things like that, where you got people that you're asking questions about, you're making an assumption that the people are going to tell you the truth. So they might say, oh, I'm going to vote for candidate A, but really they know they're planning on voting for candidate B. And that'll throw off the data if enough people do that. All right. Okay, so let's look at the last on 7.5, the very last page. Is confidence intervals for variances and standard deviations. So I'll go through this for the notes, and you can look at them on the homework. But this is not going to make the test. This one I took off of the test. This is a little too confusing for not being. So chi-square, it's pronounced chi-square. It's spelled like this. So a lot of people mispronounce it chi-square, but it's actually chi-square is how you pronounce it. So that's phonetically spelled there. So the chi-square, you have degrees of freedom n-1. But we do this for the formula. It's n-1 s squared over chi-square for the right. Now that doesn't mean you actually square it. That's the name of it. So this little thing doesn't mean squared. It's just the name of it is chi-square. And that's the right hand of it. And your variance is sigma squared. And then n-1. Variance of the sample. And chi-square for the left hand. And so this is it's tricky. It's tricky to look it up. So we'll do one example here, but we're going to do this relatively quickly. I don't want you focused on this one. N is equal to 20. S, so the standard deviation of the sample is 1.6. And first we'll find the variance, the confidence interval of variance, and then we'll take the square root of everything, all right? So we use the degrees of freedom. That's actually built into this formula. So degrees of freedom are 20 minus 1 times the 1.6 squared. And this is for the variance. And 20 minus 1 and the 1.6 squared. And now here comes the real tricky part. To find these chi-square scores. And again, you're not going to be tested on this, so I don't want you to worry, but just in case, if when you're looking at the homework problems, you're like, well, how did you get those? And you're wondering, because, you did take and pay for the course. Here's the quick explanation of that. So our degrees of freedom here are 19. So on this chart, on table G, is the chi-square distribution, but it's got a right-handed and a left-handed distribution. So there's actually sort of like two different distributions at play here. So when you look them up, you go to 19 degrees of freedom, and now you follow over, what do they want here? 95%. We're going to look up 95% and we're going to look up 5%. So we're going to actually look up two different scores. So let's go down to 19 degrees of freedom and over to 5% is 30.144, and that actually goes here. 30.144 was the 5%, and that goes here on this end, and then the 95% goes on that end. So we look up 95%. That's 10 at 19 degrees of freedom. That's 10.117. And so a lot of people get these all confused. You know what I mean? Because you're looking up two different things, a 5% and a 95%. Now, if you weren't sure like which one goes where, you know the bigger number has to be on the left because you're dividing by a bigger number. So this overall value will be smaller. So when we actually divide that out, multiply all that, divide it out, we get 1.6136 is less than sigma squared, which is less than 4.8077. And then we take the square root of everything for the standard deviation. And so for a 95% confidence interval for the standard deviation, we would use this. Now the reason we had to use a chi-square distribution for this one is because standard deviation isn't symmetric, it's skewed. So if you look in the bottom of that chart, it's got a skewed picture. And that's why you have to look up two different chi-square scores in order to solve that problem. So I don't want you to, don't fret about that problem. You're not gonna see that on the test. So that's just for homework purposes. When you're checking the homework, that's what it looks like, and that's what they're doing. All right? And that concludes 7 point, that was actually 7.3, 7.4, and 7.5. Next sections we'll cover is chapter 8.